Hi, this is lesson 3 on P1 for OCR 21st Century Science, and we're looking at beyond the solar system. So keywords for this section are light year and ways of measuring distances to the sun by the process of parallax. Now light travels very, very fast. So the speed of light is 300,000 kilometers per second. So that kind of speed, it would take about just over a second from the light to travel from the moon to the earth. Takes about 4 years to travel across the whole solar system. So from the sun to the edge of the solar system, light takes about 4 years, and takes about 100,000 years for light to travel across our galaxy, the Milky Way. So we can use the speed of light as its constant as a measure of distance. So we use, as a distance measurement, we often use light years, simply because if we use kilometres and miles, then the numbers would be so big that they'd be difficult to comprehend. So we use the light year distance, where 1 light year, so one light year is equal to the distance that light travels in 1 year. And if we look at the next nearest star to us, the next nearest star is about 4.2 light years away. So that means that the light that's coming from that star that we see tonight left that star about 4.2 years ago. Other stars are bigger distances away, and obviously we've never been to those stars. So how do we know how far away they are? Well, we use a method of measuring distance known as parallax, which I shall attempt to explain to you now. So, if we take the sun and the earth, and if we look towards a distant star somewhere over here, and the Soviet drawing is obviously not to scale, and if we look towards that star, then we will see that star by looking roughly in that direction. Now, as the Earth orbits the Sun, then we can look at that star again 6 months later, and 6 months later that star, although it's in the same position, we will have to look in a completely different direction in order to see the star. So just bear in mind, effectively we're looking down here at about 4 o'clock towards the star. When we get to here, we were looking upwards at about 2 o'clock. So this is 6 months apart. So from June, say, to December. And our method of parallax is always to ensure that we look at the star with the biggest distance from here to here as we possibly can. And this is known as the baseline. So the idea of parallax simply is that this star will appear to be in a different part of the sky in June compared with December. And we normally use the background stars, so the very, very distant stars, as a fixed background because they won't tend to move very much at all. So the idea of parallax simply is looking at a star with a 6-month interval and noticing the degree to which it has moved. Now we'll come on to look at parallax when we look at P7 and look at the mathematics of it, but essentially for now the idea of parallax is that a star will appear to move relative to the background over a 6-month period. Now the closer the star is, the more it will move. So if I had a star that was much closer, say here, then clearly when I look at it this time and I look at this time, the angle that I've moved through is much bigger compared with the angle there. So the angle that the star moves through in the sky can tell you the distance. The further away it is, the smaller the angle, the nearer it is, the bigger the angle. So we measure the angle that the star has moved through or appeared to have moved through, and we can then work that out. Now the problem with this method, so one of the downsides is that the angles are tiny, and therefore it's very difficult to do accurately and with any degree of confidence. The other downside of this method is it only really works if the stars are quite nearby. If the stars are a long, long way away, we need another method. So, parallax. Look at the star again 6 months later, work out what kind of angle it's moved through, and then you can work out how far away it is. However, angles are very, very small. We're talking about fractions of 1/1000th of a degree difference, and it only works for nearby stars. More distant stars we would struggle to see. So that's method 1. Method 2 is simply to use the brightness of a star. Now then, taking the rule of thumb that the nearer you are to a star, the brighter it appears, because the more photons are arriving, you can then make an estimate of the distance by looking at the brightness. So method 1, parallax, method 2, brightness, based on the premise that nearby stars appear brighter than distant stars. So we can fairly accurately measure the brightness of a star. However, the problem with this is that we don't know if a star, well, how bright the star is to begin with. If we assume that all bright stars are the same brightness, we can make comparisons of distance. But it turns out that some stars are much brighter than another. So particularly very hot stars are actually much brighter than smaller stars, which are a bit dimmer, and therefore that makes life difficult. So our assumption is that all stars are the same brightness isn't correct. So assumption of all stars equally bright is not true. Some stars are much brighter, so it's very difficult to know if you're looking at a very distant star or just a star that's maybe not as bright as other stars. So, two methods to measure distance to stars. We can use parallax, or we can use brightness. And just a reminder again about the idea that we use the unit of light years to measure distances in space, with our galaxy, the Milky Way, being approximately 100,000 light years across. Meaning that light that travels across our galaxy would take 100,000 years to travel from one side of the galaxy to the other. Just to compare that, it takes about 4 years for light to travel across the solar system, and about 8 minutes to get from our star, the Sun, to us on Earth.